Yes.
Great.
Okay. I think we're close to ready. Linda, are you ready?
Yes.
All right. So it's my pleasure to introduce Linda Westrick from Penn State, who's going to talk on step functions in a Weihrauch lattice. Thank you, Linda.
Well, thank you very much for inviting me, and looking forward to telling you about some joint work with Arno Pauly. So just as an outline for the talk, I'll say some words about step functions in the Weihrauch lattice. We'll talk a little bit about what should be the domain of these step functions, and go over some basic facts, and then when we can find some comparabilities between these functions. So in order to just sort of tell the story of how we got into thinking about these things, a while back, Adam and Rod and I defined a sort of topological notion that was a sort of an M reducibility, but it was not really a computability notion. Like, it was more a topological one, and it was meant to be used to compare discontinuous functions one to the other. And when you looked at the degree structure, and the definition is on the bottom, but I don't really recommend reading it, but it's just there for completeness. So if you looked at the degree structure that was made by this M reducibility, it actually sort of picked out some reasonably nice classes of functions. So all the continuous functions, continuous non-constant functions got together, and then the lower semi-continuous were like 1 degree, and the upper semi-continuous were another degree, and something like this. So that was a topological notion that was sort of involved continuous functions in its definition. And it was possible, as of course it always would be, when you ever have something that references continuity, to say, all right, let's take a computable version of this and see what happens. And of course, the computable version is going to be finer than the continuous version. So we would expect that each one of these degrees written here would split up and have a much more complicated structure on the inside. So then we asked, okay, what's actually going on inside, for example, the degree of upper semi-continuous functions? So this leads us to consider maybe the simplest possible upper semi-continuous function, which would be just a step function. So consider Cantor space, and let's put the lexicographic ordering on Cantor space so that we can make sense of having a step function there. Right. So I mean, just think of the elements of Cantor space as maybe the binary expansion of some like real number, and just make the less than follow those numbers. Okay, so in that situation, let's define the step function so that it's 0 as long as you're less than the step function at a. It's like 0 as long as you're less than a, and then once you get to a, it jumps up to 1. All right, so this is like a very simple kind of upper semi-continuous function. So then we said, all right, well, what will it, for which pairs A and B are we going to have that the step function that steps at A is reducible in this M reducibility sense to the step function that steps at B? And that sort of complicated definition that I encouraged you not to read on the previous slide, when taken just in the special case of step functions, actually comes out much more nicely. So I will show it to you. So simplification in the special case for this previous definition, if I've got 2 elements of Cantor space, then the function that steps at A is M reducible to the function that steps at B, if and only if there's just some computable way to turn an input of the step function of A into an input of the step function of B, so that if the original input is less than or equal to A, if and only if the output is less than or equal to B. Well, that's just a very nice Weihrauch reduction. So in some previous work with Kihara, we asked this question and sort of got into it a little bit, and were able to prove that it's actually quite robust, this question of for which A and B does the step function at A reduce to the step function at B. So this M reducibility was, of course, a very special kind of Wehrauch reducibility. But in fact, if you even consider sort of on the surface a much stronger way to use SB to compute step at A, which is the parallelized Wehrauch reducibility, then that's still the same. And there's even like a weaker thing where not only there is a function that translates inputs to the step function at A to inputs to the step function at B, but you can make that function be increasing or not non-decreasing, excuse me. So right. So the point of this theorem is just to say the question actually is sort of a quite robust question. So now that I've put these on here, I'll bring this theorem back in a sec. I think that everyone here is mostly familiar with Wehrauch reducibility, but we haven't had actually that many talks about it in this. So I think Selwyn used it, but it's been a few days. So a Wehrauch problem is a relation on omega to the omega, and you can have an instance of this relation, which is any x that has some thing that it's related to. Then anything that is related to x by this relation is called a solution to x. And then we say that if we have two Wehrauch problems f and g, then f is Wehrauch reducible to g if there is a computable way to translate instances of f into instances of g, and some computable function that given a solution to an instance to delta x, which is an instance of g, together with the original solution x returns solution to x. And for step functions, right, then this simplifies to say that the function that steps at A is Wehrauch reducible to the function that steps at B, if and only if there is some way to translate questions about A into questions about B, and then like a return functional that given the answer as well as the original input, sort of figures out whether or not the original C was less than A or not. All right, so it's allowed to do sort of arbitrary things, knowing the original input and whether the output of delta was less than B or not. And we say that f is strong Wehrauch reducible if there are if basically exactly the same thing, right? So on the slide everything is the same except what I change in bold, which is the only difference is that the return functional in a strong Wehrauch reduction does not have the possibility to access the original instance, right? So for step functions, what that means is that step at A is strong Wehrauch reducible to the step at B, if and only if I can translate a question about whether something is less than A into a question about whether something is less than B. But then I have this psi that allows me to sort of flip the answer, right? So maybe I could take things less than A and make them greater than B. Maybe I could take things greater than A and make them less than B, and then like switch the answer at the end. Strong Wehrauch reducibility still lets you do that. And then this M reducibility, which was the even stronger one, says no, psi can't do any flipping. Psi just has to be the identity. All right, so those are all of the. So I didn't talk about parallelization because I'm not going to really. It's just there, but it doesn't. We're not going to go into that number one, but I've just explained through 2, 3, and 4 in the context of step functions, and now this number 5 is yet an even sort of further like niceness condition beyond M reducibility. So if I go back to the strong Weihrauch, because that's someone that's similar to the M reducibility. So strong Weihrauch says we have this delta and we have this psi. The M reducibility says no, forget about psi, just like get rid of it. It has to be the identity. And now this last 0.5 says, in fact, we can make delta be a non-decreasing function. Okay, so it turned out to be kind of some notion that simplified down quite a lot to just the existence of these non-decreasing computable H's. And you can show that in all of the non-trivial cases, this non-decreasing function H actually has to map A to B, because the function that steps at A is discontinuous there. So it's going to have to use the discontinuity of SB in order to do its work. So I mean, you can make this formal, right? But just intuitively, if you have such increasing function like this, you're going to have to actually map A to B, because if you want to get then like a little less than A, you need your output then to just move a little bit and also get less than B. But then there was kind of a sort of a funny observation as well, and I'll show you sort of a picture proof of this. If B is computable, and if we're in a non-trivial case, then the function that steps at A is, and I'll use now Weihrauch reducibility to refer to this common joint concept. The step at A is Weihrauch reducible to the step at B, if and only if A is left-c.e. That's a little funny. The computable stuff's kind of above the left-c.e stuff in this reducibility. All right, so we said, kind of, what's going on? I presented this at an open problem session at one of the workshops a few years ago, but I don't think anybody really took it up. So then more recently, Arno and I decided to take it up and try to say, okay, what's going on further with this situation? All right, so let's say a few words now about Cantor space versus the unit interval. I know that I personally, when thinking about step functions, most naturally think about the unit interval. And a question that you may be having is, okay, lexicographic order on Cantor space, step functions there. Why are you doing that? Why are you not doing the unit interval? Well, of course, I'd rather do the unit interval. It just took a little bit more work to do it that way. But we can have step functions in the unit interval. And in order to deal with the unit interval, you just have to deal with representations. So fix any admissible representation that you like, giving using elements of Cantor space as names for real numbers in the unit interval. Then for Weihrauch purposes, an instance of this function that steps at A is actually not like the real number Z, but like any name for it. And then the unique solution to that Z is just what the step function at A outputs on delta Z. Or delta Z is the real number that Z represents. All right, so that sounds like kind of a mild thing, but it turned out to be rather annoying to deal with. Nevertheless, we were now with Arno, we were able to prove most of the preceding theorem, though it certainly ended up a lot more kind of annoying. And we don't know about the parallelization part or not, but at least it's still pretty robust when you do the unit interval. So just to give you kind of an idea of what the sort of extra difficulties are that you run into when you have to deal with the names, let me just talk a little bit about the 3 implies 4 direction of this. So suppose that we know that there is a computable way to translate names to names with the property that if Z names an element less than A, then that's true if and only if big delta Z names an element less than B. That delta, you can show that delta, when given a name for A, has to give out a name for B. That's again some kind of like continuity thing. Like the names for A have to map to names for B, so that if you perturb them like a little bit to the left, that the name for B can also get perturbed a little bit to the left. But this function doesn't have, this delta doesn't have to be any kind of well-behaved on names that are not names for A. So if I now start drawing a couple pictures of what could occur. All right, so here's my unit interval. Let's say here's A, although importantly, A is probably non-computable. I don't really know where A is, right? But I know that anytime I have a name for A, a name for B is going to have to be outputted. But if I have other arbitrary values, such as some C down here, there could be one name for C where a name for this value is output, and there could be another name for C where a name for this value is output. And another problem that this delta could have as well is that delta doesn't have to be non-decreasing. Right? So maybe there could be some other point right here and it has some name that's like lower than all these names that could be output for C. And then roughly speaking, the way that you deal with this is you say, okay, well, what if I do see that like for things that are in this interval here, that they have names where you can output values like this, and they also have names where you can output values like that. Well, then I just know that A is not in this interval. So I can kind of forget about delta, start ignoring it, and instead start doing whatever I want there. And same thing if you have a situation like this, where there was a decrease. So if it's possible that something here outputs a value like that, and then something here outputs a value like that, then you actually learn that A cannot be in this entire interval. Because if A were in this interval, then there would be something less than A that could output a high value and something greater than A that could output a low value. But we're not allowed to change, to flip the result. So if A were in here, then the reduction would have to be wrong, like on one of these two. So again, in that situation, we can say, oh, well, it's non-decreasing. So this whole region is, we don't know where A is, but for sure A is not here. Let's just make the function kind of do that, like on this region, and we'll be good. All right, so that's just sort of a flavor of the kind of sort of annoyances that you have to deal with when you start dealing with representations instead of dealing with the Cantor space. But nevertheless, the same thing ends up true. Okay, so fantastic. Because we got the same result in this case as well, we don't have to think about representations anymore, because for the situation for comparing the Weierach degree of step functions on the real line or on Cantor space, either one, if we want to know whether step at A is Weierach reducible to step at B, all we have to know is there a non-decreasing computable function from that space to that space that maps things less than A to things less than B, and vice versa. Okay, so now I reprise the question and hope that I have at least somewhat motivated why we might like to ask such a thing. So going forward, we will restrict attention to the unit interval. Things are just sort of a bit more intuitive to like picture and draw pictures of. However, everything that we have been proving seems to really, it doesn't seem to really care too much about whether we're using the unit interval or Cantor space. And there may even be some sort of more like general result about, some computably presented, like linear order situation. But for now, I'll just talk about the unit interval. All right, so let's talk about some basic facts about this reducibility that we can deduce by this increasing H, or excuse me, non-decreasing H characterization. So first of all, there is a notion of tt reducibility for real numbers. So we'll say that a real number A is tt above a real number B, and this is originally due to McNichol and Root. So the real number A is tt above a real number B if there is some total computable function from the unit interval to the unit interval that maps A to B. All right, so just a natural generalization of the usual of one of the equivalent definitions of tt reducibility on Cantor space. So what we learn from the existence of this H is if we do now have some H, so this one H, of course, can be the reducibility for many different pairs A and B. Like here's just one. If we have an H like this, then this H already is a total computable function that is going to have to map A to B in order to do its work. So if the step function at A is Weierach below the step function at B, then A is actually truth table above B. There's kind of a order reversingness. And furthermore, if B is not computable, it's like this H could have like flat parts in it. But if B is not computable, then we cannot have a flat part that takes the value of B. So if B is non-computable, then this non-decreasing function has to, when it hits B, has to just keep on going. So that means that A will be the only thing that maps to B. So A will be the unique element of a B computable pi01 class. So if the step function at A is Weierach reducible to the step function at B, then at least as long as B is non-computable, then A is going to have to be Turing computable from B. So in other words, in order for one step function to use another step function in any kind of useful way, the two values at which the steps occur actually have to be pretty related to each other. Even the stronger one like can't be used unless the weaker one knows enough about it to get to get A to get mapped to B. Okay, so that's first fact. Right, so based on this fact, you might wonder, okay, well, maybe the Weierach degree, so look within a single Turing degree, right? If two things are going to be related to each other, at least as long as they're non-computable, if two things are going to be related to each other, they have to be within the same Turing degree. And if there is a relation one to the other, then there is a tt reduction in the other direction. So a first question that you might ask is, okay, well, is it just tt reduction? Like, is it within a Turing degree? Take the tt degrees in reverse order. Is that what this step reducibility is? And it's not, and we can see this by a rather simple kind of example. So suppose that we have a non-computable A, which we're going to step. Just because A is tt equivalent to some B does not mean that SA and SB are going to be Weierach equivalent. And we can see this by this simple proposition as an example. So consider some non-computable A, and let's compare it with the step function that steps at 1 minus A. So A and 1 minus A are tt equivalent to each other. The function that you use is 1 minus x. But if we have such reduction as this, then A actually has to be computable. And the proof is by picture. So what if there were such increasing H mapping A to 1 minus A? Well, then H would have to be increasing function. But here, this function, 1 minus, the function that maps C to 1 minus C is a decreasing function. So they're only going to have one point of intersection, and they're both computable. So that one point of intersection, the pair A 1 minus A, will be the computable A. All right, and that's just what it says there. Sorry, I wonder if it's possible to show the other board on the Zoom. The one that I'm writing on. I think it's not showing up, right?
Was there earlier?
Oh, was there? Oh, great. Great. Okay, fantastic. Oh, thank you. Right. All right, so
Maybe you should leave that board on there.
no, I think it's good. I just because I came back and only saw myself and I misunderstood what had been happening. So excellent. Okay, so we know that whatever this relation is, that it is finer than tt equivalence. So within a tt degree, as long as we're non-computable, we will have some incomparable stuff. All right, so let's talk a little bit about this sort of funny situation, what happens when B is computable. So recall that a number is Left-c.e if you can computably enumerate the set of all rationals that are less than it. So anytime that I have a computable a number that's non-zero, just so that it's not trivial, then just like in the Cantor space case, we're going to have that step function at A is reducible to the step function at B if and only if A is Left-c.e. So proof in one direction is straightforward. Suppose that we have such increasing H, then oops. This B again. All right, so suppose that I have some increasing H. If B is computable, then I can enumerate which rationals here are less than A just by computing their values. And then if I see that it's less than this computable B, then I can enumerate that Q. But in the other direction, it's not too bad either, because we can, if we have a computable B available to us, and if we know that A is Left-c.e, then we can make H like this. So here's my computable B, and I'll start out by just letting H be like a constant function B. And then at a certain point I see, all right, here's some value that is less than A. All right, well, I'll just take the function and just change it a very little bit so that now like all those values are less. Oh, here's another value that's less than A. Okay, well, now I'll just change it ever so slightly to make all those values less than that. And you keep doing that, and you end up with this non-decreasing H that gets below B as long as its input is below A. And it has this sort of interesting like flat thing at the end. And we'll actually see later that the most interesting cases of the step reducibility have kind of some flat stuff in the H function. All right, so there were some basic facts. Now, I was mentioning that it's fairly rare or somewhat difficult, perhaps, to find instances other than this situation with the computable B. It's somewhat rare to find instances of strict comparability between the step functions. And so let me show some more examples of this. So first observe that if the step function at A is Weierach reducible to step function of B via an H that is actually invertible, then the reduction for the step function reverses as well. Because if that function H is invertible, then its inverse is also a non-decreasing function that now maps B to A. So in order to have any kind of strict inequality between SA and SB, it has to be the case that if the step at A is reducible to the step at B via some H, as long as B is non-computable, all right, so if B is non-computable, there can't be a flat part right here. But there will have to be lots of flat parts to the function kind of all around. Because even if there were any interval around A where the function were invertible, then you could just kind of fix the function outside of that interval, and then it would be invertible. So if we want to find any kind of strict increase, we'll have to have a function that has a lot of plateaus in it. Just because you have reduced A to B using a function that has a lot of plateaus, though, doesn't mean that those plateaus were strictly necessary. So let's consider what happens when you take an H that has a whole bunch of plateaus and you just try to invert it. It's not going to be a function, all right? But then we're going to try to fix it in order to make it a function. All right, so suppose that I've got this, so here it's going to go straight up, straight up, straight up. All right, so suppose that I have, this is my like J inverse, that's not a function. So suppose that the step function at A is Weierach reducible to the step function at B via some J. And here I've drawn the function J inverse, which is not a function because it has a lot of vertical segments in it. And I want to show that in this circumstance that B is strong Weierach reducible to A. Well, I won't always be able to do it, as I'll show you later. But if it turns out that A and B are actually Turing equivalent, then we can fix this. Excuse me, tt-equivalent. Then we can fix this by just using the fact that we also have a total computable function that maps B to A. This other total computable function, it may not be increasing, right? It may be some like weird function. Okay. So maybe that's my total computable function that maps B to A. But now that I have this B and this non-function J inverse, if I look at all of the points where those graphs intersect, then because all of those points are on J inverse, they have to be increasing. But because this G that shows the TT reduction from B to A is actually a function, all of the points that are on the intersection have to, you can't have one, vertically on top of the other one. So you have this pi01 class, like on which the two graphs agree. And then in between that pi01 class, to construct a reduction, an increasing function reducing B to A, you can just fill in like between those points in some increasing way, and that will work out. All right, so in some instances, even when the reduction from the step at A to the step of B has many flat parts and you invert it, it's sometimes possible to repair that and still get an equivalence. All right, so there's some situations where there's a situation where when you have a Weirick reducibility in one direction, if you have even a TT reducibility in the other direction, then you get a Weirick equivalence. All right, so there is a kind of equivalence between A and B that is implied by the existence of a Weirick reduction between the step at A and the step of B. So say that A and B are Bicut equivalent if the collection of rational numbers less than A is enumeration equivalent to the collection of rational numbers less than B. And similarly for the rational numbers greater than A and B respectively. So suppose that we've got a reduction between the step function of A and the step function of B. Then as long as A and B are not computable, then A and B will have to be Bicut equivalent according to this definition. And that again just comes directly from the existence of that function H. Right, so I sort of draw the same picture again and again, but somehow, So if I have some function H like this, and I'm able to enumerate like everything that's less than A, then I'm able to enumerate everything that's less than B. Similarly, if I'm able to enumerate everything greater than A, then I can enumerate everything greater than B. Right, so this function, sort of no matter where the pair AB lies along it, this function gives me in both directions, actually, a way to transform positive information about things above A to positive information about things above B, and similarly for below. So that's actually if you remember back to the example with A and 1 minus A, that was sort of an example where the two sort of failed to be Bicut equivalent. So this Bicut equivalence is a property that anytime that you have the strong Weirick reduction in either direction, then you get Bicut equivalence. And it's finer than TT reducibility. Okay. Right, so then we're able to show that, so theorem, I say theorem asterisk. Okay, so we have come to the part of the talk where the theorems, although thought about carefully, have not been written. So I put an asterisk so that you know to take with a grain of salt and ask me later if it still worked when we wrote it down, but we believe that it does. Okay, so if A and B are hyperimmune free, then in fact, not only can you, if you have a reduction in one direction, does that imply a reduction in the other? This would this would already follow from in hyperimmune free degrees, Turing reducibility and TT reducibility coincide. But in fact, the only thing that you need in order to know that two hyperimmune free reals are equivalent in terms of their step functions is if those reals are Bicut equivalent. So let me give kind of, again, sort of a picture sketch of how you use the fact that two hyperimmune free reals are Bicut equivalent in order to show that you can make reducibilities either way with the step functions. So suppose that A and B are Bicut equivalent. That means that there is some algorithm, which if you start giving it rational numbers and say, these are less, these are less, these are less, then that algorithm will give you other rational numbers and say, those are less, those are less, those are less. Right? So A is going to be there, but there is an algorithm that doesn't know what A is. But just for anybody, let's say here's like some C. They'll say, oh, this is less than C, then the output should be at least this big. Oh, this is less than C. The output should be at least this big. This number is greater than C. Oh, the output should be at least this small. Right. So for any possible input, there are a pair of reductions already existing. Those reductions that work for A and B that will, just based on what you know about C, will sort of tell you, oh, well, the output should be at least this, it should be at most that, at most that. And if C is equal to A, then actually the reduction has to work properly, right? It has to go up, 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 and it has to go down, 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 and it has to meet right here at B. Now, at other values, the reduction that worked for A and B does not have to work properly. Right? So a few things could happen at arbitrary values C. You could get a convergence to some value, or it might just sort of peter out after some point and leave a gap. Or the two enumeration reductions could create an overlap, contradiction. The last case is easy to deal with. If the two, if you're looking at some point, and our goal, right? Our goal is to create. All right, so let's erase this now and just say at this C there might be like a gap. So at some points it'll be exact, and we want to make an increasing function that preserves the exact points. That way we'll make sure that A gets mapped to B. And when there's a gap, we just want to go through the gap like somehow, not too worried about it. If there's a gap, then A is not there. And what should we do if the two actually overrun each other? Well, then also we can do whatever we want because A is not there. If the two overrun each other, then we can see that happen. Say, oh, now I know that A is not there. I already know that I can do anything that I want. The problem is, of course, when there's like some region where there seems to be a gap, because it's just an enumeration reduction. So right now there's a gap, but a million years from now the gap could close. So now finally we use the fact that A and B are hyperimmune free. Because if A and B are hyperimmune free, then not only is it the case that the gap is going to close at A, but there's going to be a computable function that tells you how long you have to wait for that gap to close. So you can use that computable function and say, okay, well, if this gap has not closed by that time, then again, I can just do whatever I want inside of this interval. Oh. All right, so we've seen two examples of situations now where as soon as you have a Weihrauch reducibility in one direction, then you get one in the other direction. Those are in the case of if you're inside a single tt degree, or if you're hyperimmune free and you're inside a single Bicut degree, you don't even need one direction to get started. You can just use the Bicut equivalence to make your H. All right, so far we've got a picture that really just has a lot of either stuff that's the A comparable to B and B comparable to A, or just no comparison between the two. So I want to finish by saying that sometimes, nevertheless, we can find strict comparability for this relation. And for that, I want to return to the those Left-c.e reals, just because in order basically, in order to make some strict comparability, we have to do a construction. And the easiest way to do a construction is to make something, to construct a CE thing. Yeah. Okay, so first, just observation. So suppose that I've got two Left-c.e reals that happen to be in the same Turing degree. All right, so just right, or orientation, right, where we are kind of. We've shown that there is like some degree of the step functions at computable numbers. And the things that are below that are, in some configuration, exactly the Left-c.e reals. And then we also had just a bunch of other stuff, like here's some like hyperimmune free stuff that's incomparable to each other. So this is like stuff out like to the side as well. So lots and lots and lots of like incomparability in the step degrees. And what we're trying to think now is, okay, well, is there some comparability? So let's consider the part that concerns the Left-c.e reals, and consider a single Turing degree among these Left-c.e reals. So I'll draw the Turing degree, maybe like this. So in order for things to be comparable in the sense of the step function, they all have to be in the same Turing degree. So the interesting thing about the Left-c.e reals, you can observe that if A and B are Left-c.e and even in the same Turing degree, then they're already Bicut equivalent. For Left-c.e reals, the left part of each of them is just computably enumerable. So they're automatically Bicut equivalent on that side. I guess they're left-cut equivalent because you can just enumerate each of them. And if B computes A, then that means that using both information of what's less than B and what's greater than B, you can get information of what's less than A and what's greater than A. Well, the information of what's less than B is free. So really you're saying just given positive information about what's greater than B, you can compute positive information about what's greater than A, and vice versa. So if I look at one Turing degree of Left-c.e reals here, that one Turing degree is actually also one Bicut degree. So we can hope possibly inside of there to produce some strict comparabilities. And indeed, that is a thing that we are able to do. So there are Left-c.e reals A, B, and C in such a region that make a shape like a V. Yeah. So the step function here at C is going to be smaller. It's going to be reducible to the step function at A and also reducible to the step function at B. But we'll make sure that A and B have have incomparable Turing degree, so that A and B are incomparable. And then that means that both of these inequalities will have to be strict, because if they were equivalent, then we would have a Turing comparability between A and B. All right, and so this is a finite injury argument, but basically the way you do it is just say, okay, we're going to build C to be like Left-c.e, and then we'll just build two functions, HA and HB. And the idea is that and they're going to be increasing functions, so they're going to be this kind of reductions. And then the idea is we'll just plug C in, and whatever comes out of HA will be A, whatever comes out of HB will be B. And so then you read these requirements like in that way, right? So to say that A does not TT compute B, then we need to satisfy that anytime phi E is total, if I plug A, what's ultimately going to be A, into phi E, then I don't get B, and vice versa. So just to give a little sketch about how these requirements work, like how can we satisfy like one of these requirements? Well, what we want to do is imagine that we're working in some interval And the construction's been going on, and C has gotten up to here, to the left edge of this interval. And now the requirements are going to try to go to work inside here. So let's say I'm going to look at RAE. So RAE is going to be given an interval in which it can control HA and HB and try to make stuff happen. And if it succeeds, then it's going to move C into here. So how it's going to do this? Well, whatever HA and HB were doing inside this interval, all we know so far is, whatever we've done, it's been kind of increasing. So HA and HB will look something like this. So then what we're going to do is say, all right, divide that interval up now into some like very fine segments. And we'll make HB within that segment go flat and then a little up, flat, a little up, flat, a little up. And so that the endpoints end up the same and the wiggles are small enough that we're still allowed to do it. And we can do the same for A, but opposite. So let's let HA go up, flat, up, flat, up. Okay, so whenever one of them is linear, like increasing, the other is flat and vice versa. So now suppose that we want to try to force phi E to make a mistake when using A to compute B. Well, anywhere that HA is flat, phi E of HA. So imagine that we moved C into one of these places where HA is flat. Then the left-hand side phi E HA of C is going to have to be not changing. But in that same region, B will be changing a lot. So at a certain point, if we wait long enough, then phi E will have to continue converging and eventually, find some interval where that equation, or where that inequation definitely holds. And then this requirement can say, great, move C into here, specifically move it into this region, specifically move into the subinterval where we saw that guy failed, and then we'll continue the construction from there. Okay, so that's just a small sketch about how defeating this kind of requirement works. All right, and you can do the same thing actually with some similar requirements to build strictly increasing chains. Right, so if you just say, all right, I'm going to build C, and then there's going to be an HB to make B, and then there's going to be an HA from that to make A. You can write down some similar kind of requirements and satisfy them. All right, so you can combine that with finite injury. And it turns out that these requirements and the ones from the previous, and also coding requirements and also permitting stuff, all like play well nicely together. So putting that all together, we can show in any Left-c.e Bicut degree, which is the same as a Turing degree. You can find a whole tree of Left-c.e reals indexed. You can find a whole collection of Left-c.e reals indexed by omega to the less than omega, so that anytime that you have a strict increase of your element of your tree, then you get a strict step reduction, and you get Turing incomparability or step incomparability, like whenever the elements of the tree are incomparable to each other. All right, so there is lots of strict incomparability around, at least in the in those nice like Left-c.e degrees. You just have to go looking for it. All right, and then here are some references that I mentioned. Thank you.
Very nice talk, Linda. Any questions? Let me bring the mic over.
Right. I might be missing something big here, but so in the initial setting, how did you get to? I mean, you said that SA Weihrauch reduces to SB implies SA Weihrauch reduces to the parallelization of SB, and those things are equivalent. Is that correct? Could you give an idea of how you move to? I mean,
so in this
parallelization,
to the omega case.
Yes. So how you go from 2 to 1 essentially?
Yeah. So
well, actually, yeah.
Yeah. So suppose, so you have to use. So the first step is you have to use the fact that because of the fact that SA, all right, so imagine you have a reduction to the parallelization. Take some name, or no, we don't even need a name. Great, this is just Cantor space. So take A and input that into that reduction. And so watch the reduction the whole way through. What happens for A? Well, A uses some fixed finite number of the, so you have these infinitely many like queries to SB. But when you follow through what happens with A, it only uses finitely many of those. You look at those finitely many that A actually uses, and you find some of them are essential and some of them are not essential. And the ones that are used that are essential are the ones with the property that that function, the forward reduction mapping A to the input there has to map to B. And if you put anything a little bit less than A into it, then those ones coming out of SB would be zeros. So you'd identify which one of those are essential. And then you see that, okay, if A is the input, then all of those essential guys have to be 1. And if the input is a little less than A, then at least one of those essential guys has to drop less than B. And so then if you take the minimum of all of those essential guys, then you get a function not necessarily increasing that does map A to B and maps everything less than A to less than B. And then you can also fix that function to make it increasing by taking some just like supremum of everything less. Like if you want to, the function now that we desire is on input X, look at everything less than X, look at the minimum of all of those sort of essential guys on inputs less than X, take the supremum of all those, and that will be something that works. Yeah.
I was wondering if like the same thing that you could do for left-c, you can do for right-c in kind of a reverse way, or it is completely different?
I guess when it's Left-c.e, you can make this. So consider the case where B is computable. When it's Left-c.e, I have the ability to sort of change this function to go down below A, but then at A, it's still going to be equal to B. If I tried to do a similar thing, but like coming from the right, then I'd be able to change this part of the function, but not that part of the function. So I'd be stuck, right? Like the values here would always still be B, which is too big. So the way in which there's a symmetry is we made one arbitrary choice when considering step functions, which was to consider the upper semi-continuous ones. Right, so at A, let's see. So yeah, so the things at A, the value of the step function is 1, not 0. But if we reversed that and made at A the value of the step function is 0, and then proceeds to 1 only for X is strictly greater than B, then we could get the kind of symmetry.
Yeah, so just in the hope of getting a more concrete example of strict comparability, what would happen if you take, say, your favorite Left-c real, say, take omega, and then you take the Turing join with 0. So you insert a 0 in every other position. So, well, you will be, the first one is going to be lower or equal than the second one, because while inserting zeros, it's a strictly increasing function, but it seems that doesn't reverse. Deleting every other bit, that's not increasing. So can you say anything about how they compare these two?
So for any real A, if I take A and I take A join with all the zeros,
Yeah.
those two reals are tt-equivalent.
Right.
So assuming that you got a reduction in one direction, then you will have in the other.
Okay, that was on your side. Yeah. Okay. Yeah, that's surprising. Okay.
Although actually, I will say maybe just small asterisk for that because now we're talking about Cantor space.
Right. Yes,
And
that's essential.
we did everything for interval and then said, oh, I think it works for Cantor space. It should be checked. Yeah.
Okay, thank you.
I have a question. So you did it for one discontinuity. Do you think you can say something for multiple discontinuities?
We didn't get to that point. Yeah. I mean, I'm sure something could be said, but I didn't have any thoughts about it yet.
Other questions? Well, let's thank.
I don't know if Arno had any thoughts about multiple.
My expectation would be that already doing something like this finitely many points of discontinuity would interact with the complexity of the picture that we have, that I don't think I want to do it.
You can always start with 2 and see if it blows up, right? Okay, let's thank Linda again for marvelous talk. Start again in order after 11:15.
Yeah. Okay. Okay. All right, take your time.
Can we give everybody, Peter? Sure. You don't have to do it.